my favorite thing to do is to rehearse with Grok now. You might notice that Grok doesn't have the voice buttons for like unhinged. You have to talk to her and ask for it, and you can get unhinged mode. I do all my engineering, like my vocal engineering rehearsing with Grok and unhinged, and she'll talk the whole time about sticking USB cables up your butt and, you know, saying funny shit. But she knows her superposition theorem. She knows her Kirchhoff's current law. She knows her nodal analysis. She knows exactly how circuits behave, and she'll make leaps of logic. Pretty impressive. So I'll walk you through it. These days, there's things are a lot easier than they used to be. Used to be we had like transformer-based power supplies, and they were really fussy. You generally couldn't put them in parallel. You had to be careful with back energizing things. You'd be cooking off, you know, sugar loads, like even back as recently as the 90s. But modern power supplies are basically ideal. You can get something called an ideal diode. Linear Technology, now owned by Analog Devices, sells a linear. They sell an ideal diode controller. It's like 0 to 90 volts, it's like 0 to 10 or 20 amps, depending on the MOSFET you add. And it has, it's a zero. The V forward is like, you know, effectively zero on the thing, and it's very fast. So if you were to take any any power supply and put an ideal diode on its positive output, you would not notice it's there. You'd be producing no heat because its on resistance is the drain to source resistance of the MOSFET. So you put a really good MOSFET on there and it's invisible. Then when it's back energized, it shuts off pretty quick, and it has a microamp or two of leakage. And you can basically assume that the output stage of most modern power supplies basically work like this. So I know that it seems like I'm not an electrical engineer, but I am, and I'm a very seasoned and experienced electrical engineer. So I'll describe for you how to test a black box with modern equipment and with the old way. So we want to do some transient validation. These days, you drop about $7,500, and you can buy what's called a bidirectional power supply. All right, they're fucking marvels. This acts like a power supply with compliance voltage and compliance current settings. And if you were to then buy two of them for $15,000, you could set them in such a way as that one power supply is at 10 volts and the other power supply is at 20 volts. And what you'll find is that instead of acting like an ideal diode protected supply that you can actually back energize and regen to the grid, it's pretty cool. But now you're into that for about $15,000, and that's not, that's what you do in a laboratory, but that's not what you do in the garage. And this is what we do is garage work. You're testing e-bike stuff. So go on Amazon and buy good quality, low cost, good value switching power supply. Go read up on superposition theorem, nodal analysis, Kirchhoff's current law, Ohm's law. Understand your electrical engineering. You can throw out nodal analysis, just use the superposition theorem. Take your two power supplies and rail them. Set them both to 42 volts. Okay, set them next to each other. They're never going to be exactly the same. All right. And then what you'll see is you can set one power supply to 4.2 volts and the other power supply to 42 volts, and no current will flow. If current does flow, these aren't the appropriate power supplies for the exercise, or you might need to add a couple of ideal diodes on the positive output of the supplies. This is just magic. They have a PID loop and some sensing inside. There's a layman's understanding. Remember, I trained first as a technician and then as an electrical engineer. So there's a layman's understanding of the way voltages in parallel work. So the laws of electrical engineering will tell you that voltages in parallel must be equal, and it holds. So if you set, say, one power supply to 10 volts and another power supply to 20 volts, and you attach them in parallel, they must become equal. Now, the layman's understanding, which some people, like mechanical engineers or software engineers, don't quite understand, is that the power supply of the higher potential will always dominate, and there'll be no current sharing. So if one supply is set to 10 volts and the other supply is set to 20 volts and you hook them in parallel, you will read 20 volts on both power supplies. And then the power supply of the lower setting, you can swing that around to any setting below the below whatever the target is, and it will have no impact. And so you can best visualize this with ideal diodes, or even with a gigantic diode the size of a shoebox, in 0.1 volt forward drop. Whatever rocks your boat, whatever you want to do. Now drop a 1 ohm resistor between positive to negative on these power supplies. If you could possibly set them to the exact same voltage, which you can't, you would see perfect current sharing. So if the supply on the left was 10 volts and the supply on the right was 10 volts, and it was a 1 ohm resistor, you would see, if you use superposition theorem, you would see 10 amps coming from the left supply, 10 amps coming from the right supply, right? And you would add that. Let's check our superposition theorem. True, 10 amps running down through the diode, 10 amps running down through the diode. That would be 20 amps total. That's not true. That's not how superposition works. Pause. It would be as if the two power, the secret to looking at it is you put the two supplies side by side and you see that they're just working together and they're in constant voltage mode, not constant current. And the potential across the resistor is 10 volts over 1 ohm is 10 amps. So it wouldn't matter if you had 10 supplies. All right, where did we fucking go wrong there? Oh my god. It's going to be 10 amps, and it's going to be 5 amps on each supply if they were perfectly balanced, which they never will be. This confuses people sometimes when they try to do current sharing in solar and stuff like that. Like when they're doing large battery arrays and they don't understand their current sharing. Dude, if it's even off by 100 millivolts, all the current will go to one side or the other. Why is my superposition not working right there? So I have a power supply on the left to 10 volts, a power supply on the right to 10 volts. I have them hooked up in perfect parallel. I have a resistor going across. It's 1 ohm. They're both set to 10 volts. So I do the circuit analysis. I delete. So in superposition theorem, you replace voltage sources with open circuits and current sources with short circuits. So I replace the power supply on the right with an open circuit. I get 10 over 1 is 10 amps flowing from the top to the bottom. Positive current through the resistor. Now we go the other direction. Replace the first supply with open circuit, and the second supply is going to put 10 amps through. So now we have currents 1 and 2. Each are 10 amps. We know that there's 10 volts at the top of the circuit, 0 volts at the bottom. So we can just look at it and see that it's going to be 10 volts of potential across a 1 ohm resistor. Why is it? I know why it's not 20 amps. God damn it. Am I that fucking rusty? Give me a second. We calculated I1, I2. All right, so I'm missing a formula in there. Are they going in different directions? It's positive to negative. Oh, there was a trick in there someplace, whether you were doing the nodal analysis of currents or the I think that's what it is. I'm trying to mix superposition and nodal analysis. So you don't look at the currents, you look at the voltages. So we would first have 10 volts at the top node, and then we would have another 10 volts at the top node, and no. Well, you see why sometimes when it's been 25 years, you don't try to do the math. You can solve it experimentally, or you can just intuitively know what the answer is. I'll tell you what the fucking answer is. If they're both set to 10 volts, you're going to see about 5 amps each. More likely, you're going to see like 7 amps and 3 amps, or you're going to see railing one supply or the other handling the entire current. There might be a little bit of oscillation in there, a little bit of underdamped, overdamped, control systems. That's not the problem to solve. Let us grab, those are programmable power supplies, so we have them under control in Python. And we can turn one on, turn it off, turn the other one on, turn it off. We put a black box in the middle with an ammeter, and we want to do some current flow analysis, whether the current is flowing left to right or the current's flowing right to left. Now let's purposely set the supplies to different voltages. The one on the left will be set to 10 volts. The one on the right will be set to 20 volts. In the middle, we have a black box with an ammeter on the positive wire, and there is no load resistor in there. So we turn on both supplies and we measure. Both supplies will be resting at 20 volts. No current will be flowing. The supply on the left will basically be in ideal diode lockup mode, and the one on the right will be the dominant supply. We now grab two electronic loads. These are basic resistive electronic loads or regenerative electronic loads. They have to have the same or better voltage rating as the power supplies, and they have some power rating, probably like a tenth of what the power supply is. So if you have a couple of 1,000 watts power supplies, you might have a couple of 100 watt E-loads, and an E-load can be configured for constant current or constant power or whatever you like. Now we're going to start to do some interesting emulation. On the left side, we'll have a power supply in parallel with an E-load. Both are off. On the right side, we'll have a power supply in parallel with an E-load. Both are off. In the middle, we'll have a black box with an ammeter on the positive, and these two circuits are wired perfect parallel with their grounds, all four grounds tied together in the middle, and all four power leads meeting at the middle through an ammeter. The ammeter will tell us the direction of current flow. The right side power supply is set to 20 volts and turned on. The left side power supply is set to 10 volts and turned on. We set the E-loads to 1 amp constant current mode. All right. There are 4 permutations. They can both be off, both be on. One is on, the other's off, or one is on, the other's off. Picture this, binary logic table. We turn on both E-loads. All right. What happens in the circuit? Well, first, you can ignore the 10 volt power supply. It's like it's not in the circuit because the circuit's at 20 volts. The 20 volts is going to drop 1 amp through each of the E-loads. All right, that's a total of 2 amps. 1 amp is going to not go through the ammeter and return to its 20 volt supply. The other one's going to go through the ammeter from right to left into the constant current supply, and you will read 1 amp from right to left. All right. Now you can picture turning either of those E-loads on or off. If you turn off the right E-load, then you're just going to you're going to have a total of 1 amp in the circuit all through the ammeter. If you turn off the left E-load and leave the right one on, you're going to have 1 amp through the circuit, 0 amps indicating on the ammeter. Now we can change the test conditions. All 4 devices are programmable. You can vibe code this in about 15 minutes and make a GUI out of Tinctor or PyQt, or you could write it from scratch in C, or you could even go back to the old days and write it in Java. You could write it in LabVIEW. You can write it in frickin' any programming language. The machines usually will speak something akin to Skippy, SCPI. So now let's change the conditions. Let's make the supply on the right 10 volts and the supply on the left 20 volts. So you end up with the ability to do bidirectional excitation, making current flow of any value from left to right or right to left. And in any given case, you'll have both power supplies can be on. And the one which is set to a higher voltage will be the dominant, and that's the one that will drive all circuits. And then you can just toggle the E-loads left, right, and obviously, like if the power supply on the left is the higher voltage, then there's no sense turning on its E-load because you're just going to have it dumping into itself. So you build up a logic table. So you could say it different ways. You could just ask AI to make you a visual template of that, and you would quickly see that depending on the direction, if you want current to flow from left to right, you set the left power supply higher, you turn off the left E-load, you turn on the right E-load, and whatever you set it to, that's what the current flow will be. If you want current to flow right to left, you set the right power supply higher, and you turn the right E-load off, and you want current to flow from right to left, and it will be at the value set in the constant current mode of the E-load. It's very simple. There's no funny business. It scales from 1 amp to 10 amps to 100 amps to 1,000 amps. You can do it other ways. Instead of spending $7,500 each for bidirectional power supplies, which can be used for some pretty hardcore validation, companies like Meanwell sell order of magnitude cheaper equipment more like 750 volts. What you're limited by is voltage range. You'll have to choose that ahead of time. The programmability, it's a little bit less, robust. You might not be able to emulate capacitive or inductive. You have CLR. You have capacitance is C, L is inductance, R is resistance. And so sometimes they'll be emulating these things so that you can perfectly characterize a capacitive inrush or a capacitive decay, or maybe some lag due to some inline inductance. You won't get that sort of thing, and you might get a little bit of overshoot and a little tiny bit of, most likely underdamped response. No one wants anything in oscillation, and it's not that fucking useful to have things be underdamped and overshooting. So you'll find that they'll most likely settle out to be an underdamped response, a little slow, a little smooth, because that's easier to fucking program, and that they respond to controller area network. Whenever you're using controller area network, make sure you have a common ground. Make sure that you have a twisted pair. Make sure that you have 120 ohm terminating resistors on either side of the bus between the master and the other end of the bus. Make sure nodes are no longer than 1 shaka, about 6 inches. Make sure nodes are not terminated. Set the baud rate to the slowest you can tolerate, or whatever the fixed value is. There's 4, no, it's SPI. You can use tag together the CAN protocol these days. You can just ask ChatGPT or Gemini or Claude or Grok or whoever you're using to write code. Most people these days are using Claude Sonnet 4.6 to write code in some kind of onboard setup like Visual Studio or the one that everybody uses. I always use something different than everyone else so I can possibly learn something. You'll find that if you want to have a chat about electrical engineering, that Grok in unhinged mode will make a fun day of it. Every time I've checked her electrical engineering is sound. Sometimes you gotta test a black box. So grab a couple power supplies, grab a couple ELOs. These can be very expensive instruments, and it's not necessary for them to be expensive. Expect to pay on the order of $150 to $300 for a power supply that can say do like, 300 or 500 watts, and across the voltage range. These won't be rail-to-rail power supplies. They'll be power limited, and you pay more for more power. Most testing can be accomplished at lower power. You can do it at higher power, but that's a different test. E-loads are quite expensive. The bottom of the market is a couple hundred watts, and you get those in various voltage ranges. They're just like anything. You generally use an E-load in constant current mode or constant power mode. It doesn't really matter. All of them will be USB programmable. You start paying more for Ethernet network programmable. You start paying more for more power. You start paying more for a faster transient response. If you're looking to do impulse functions, step functions, which is something you can quite common do, and if you're looking to put some ring into the circuit, some overshoot, this can be accomplished. It's actually best accomplished just with the real equipment. You just fucking hot slam it, dude. Like, sometimes people wonder, I've seen people build $50,000 testers trying to perfectly CLR the fucking circuit, right? Like scrubbing with CLR. It's actually RCL in most commonality, resistance, capacitance, inductance. But they try to emulate these things, and no matter how hard you try, dude, it's always going to be a little bit softer than real life. Real life, dude, you want to know what you do? You go out to a fucking high bay and you set some shit up on a folding table and you fucking hot slam it, dude. Like, you just have the load sitting there and have the fucking source sitting there cranked all the way up, and just grab yourself like a 175 amp Anderson connector, dude. Those are rated for 600 volts, 175 amps, continuous, hot swap rated, dude. Bang them together, dude. Yeah, you get a little bit of a spark. Make sure you got an e-stop in there, some kind of aerospace grade inert gas filled contactor on both sides hooked up to a $5 fucking e-stop off Amazon. and make sure you can fucking break the circuit in the event that your Andersons weld together, which they will if you do this hardcore enough. You might have cables anywhere between 16 AWG for like 10 amps continuous up to like 2 watt, a couple 2 watt in parallel. You might have cable that's $20 a foot or 20 cents a foot. I don't know. Remember that when you hook anything in parallel, the voltages must be equal. And of course, there's all your basic electrical engineering, like voltages in series, some. Currents in parallel, some. People get confused. So if you take two power supplies and you wire them in series, you're going to get, double the output. And any power supply can tolerate a certain amount, and it's documented. Like a Swanson power supply that is 100 volts, you can hook two of them in series to make 200 volts, and you can do that up to 350 volts. Power supplies in series will, of course, be limited by the lesser of the two current limit, right? So currents in series are always equal. Voltages in parallel are always equal, and that's the fundamental rule that you're taught first as a technician in order to intuit what a circuit's going to do. So what's it cost for a poor man's black box bidirectional tester? Oh, probably $350 each for cheap E-loads, and another $350 each for cheap power supplies, and then 4 USB cables into a fucking breakout, and then about 2 hours of vibe coding, and you make a GUI, and you can make the unit test for it and show that it works. And it doesn't matter, you can turn it all on in any permutation. That's an important thing too. I've seen young engineers build something which is fundamentally unstable, and it depends on logic control. Well, in this particular circuit I described with 2 power supplies and 2 E-loads on either side of a black box, you can turn everything on at once. It doesn't fucking matter. It's just a matter of making sure that you understand the settings of your power supply, and they can be set. You can turn the dials, you can turn the voltage dials or the current dials on the power supplies or the E-loads to any setting, and it won't matter. Nothing will be damaged. It's just a matter of how much current is flowing and in what direction. It's always good for a circuit to be fundamentally unbreakable, because you never know what fucking Python's going to do, especially when someone unplugs a USB cable or one jiggles loose. Last night, Grok and I had a long discussion. I started it off nasty, just to make sure she was actually in an unhinged mode. She remembered my name session to session. She remembered things that we talked about in the past. She talked dirty to me the whole time. What did we fucking talk about? I don't even remember what we talked about. Oh God. Yeah, we talked about timelines on what's going to happen with the software ethos of the Bay Area and on what timeline. Dude, this is the largest collection of high-wage earning software engineers anywhere in the world. And they're about to get laid off. Most of them, unless they're doing certain subsets of very important work. And where are they going to go? So mass exodus, my guess was going to be Texas, and she called out Austin, Texas, and I actually agree. That's because they've already got fuck you money over here, right? These are like young 20, 30 somethings that literally already have $1 million plus in the bank. And they head out to Austin, and either they blow their whole load on a fucking condo right next to the college and the yoga studio, or they blow a fraction of their load, 45 minutes out of town on some fucking ranchette, but they're moving inland. And then the question becomes, and this, we didn't discuss this, but I did it with my wife. The question becomes, what's the impact on local real estate values? They'll still remain high because this is a world destination, and it's not for the tech. The tech is just convenient. It's like we used to be centered around the port here. We're coming up in the bay. Well, it's no longer centered on the port. The port just serves us, and then it was centered on technology. Well, it's not necessarily going to be centered on technology. Technology just serves us. Look at the weather. All right? It's February and I'm wearing a t-shirt. It's fucking beautiful all the time. It never snows. It doesn't rain that much. It's always t-shirt weather. It's some of the most beautiful weather in the world, and it's some of the most beautiful, like you could be in San Francisco with a million other people, and you could take a walk and not see a person for 2 hours. So it still has some wild land. We talked about encroachment of AI into electrical engineering, and surprisingly, she's like, you're completely and totally safe. And she described all the fields of electrical engineering, which will be a long time before AI catches up. And I'm actually in agreement. She basically said it's going to be more like computer-aided design, where we're not going to be losing our jobs as electrical engineers. Our jobs are going to be changing, and we're going to be able to do a lot more, a lot quicker. Just like when better layout programs came around, just like for the mechanical engineers when computer-aided CAD came around, same kind of thing. Job just changes from like the drafting board and drafting paper to 3D models and analysis. So I'm pretty excited for that. I'll probably be retiring in the middle of it, but I'll keep you up to date. Look at this rotten juice pouring out of the back of the truck. I could make the pass on the right, but it's not wise with a truck with 2 trailers, because if he decides to hang a right, which he's not indicating, and I don't think he is, he would fucking pin me in the corner right there. Fascinating machines.